Okay, hello, good morning, everyone. Happy to have you here. We're all set up for our sixth webinar. It's been half a year of webinars right now, as as we've been reminded recently. So on today's webinar, we have an exciting lineup of topics. So we have Dhritiraj Sen Gupta, who's a PhD candidate in a university in China, and he's going to be talking about coastal land reclamation patterns, which is his area of his domain of research, and how he's used earth engine within his work. Besides that, we also have Pradeep, who will be talking a little bit about getting started with SAR and microwave imagery. We've noticed a few requests coming in for SAR and people who are interested in SAR but not quite sure about how to get started with it. So we're hoping that users will find that useful too. Before that, we just like to mention briefly a little bit about the Earth Engine India community volunteering positions. So I'm going to share my screen quickly. Yeah, so as you guys would know that the Earth Engine community in India depends heavily on volunteers, and so far we've been able to do a lot more than we expected in the initial few months, with each of us putting in our little time here and there. Each of us use Earth Engine in our work, but we're also interested in the broader community and of users and getting people engaged in and around Earth Engine for positive impact in India. So we sent out this mail a little while back. We'll be sending it out again later today. This is basically a description of the different positions, volunteer positions that are available and open for people who would like to apply to be part of the community in a volunteering capacity. Um, so there's community organizer, there's the Earth Engine India Media Committee, there is community on air host where you would be engaging with us here to help us host and moderate and curate content for these webinars. There's code curators. So those of you who are interested in the code itself and would like to help come up with example scripts for the community repositories to help other users get started. Um, and there's website managers. So the Earth Engine India community website, which becomes a focal point for many people when they first hear about the community, working to help develop that website a little bit. We've put out a form for users who are interested in joining up. So this is what the form looks like. It's not at all comprehensive, and it's not at all daunting. It's just literally asking you just your email ID, what position you're interested in, and what motivates you to join the community. So we definitely encourage you guys to, any one of you who feels like you would like to do something, pitch in a little bit here and there. Um, we'd encourage you to sign up on this form. We've shared the links in today's slides, but we'll also send out an email later today. We've got 3 responses so far already. So Guneet and Soumyakanta and Vaibhav. So we'll be hearing, the community will be hearing a lot from them too, in their capacities as volunteers. And yeah, we do hope that more of you will come across this and decide to sign up. And looking forward to that. Um, so I'm gonna So without further ado, let's go ahead with Dhritiraj and his presentation. So uh, we'll be sharing links to today's slides in the YouTube live stream. So you guys can follow along there. Do feel free to note down any questions that you may have and type out those questions in the same YouTube live stream window, and we'll be getting to those questions at the end of the webinar. So go ahead, Dhritiraj.
Thank you so much, Craig. First of all, thank you so much to the entire Earth Engine in India community. It's a fantastic platform for students, for everyone to come along. Without delaying, I'll share my presentation. Am I audible? Hello?
Yeah, Dhritiraj, we can hear you here.
Yeah. Okay, great. Sorry. It's just perks of living in China. I am a PhD student at East China Normal University in Shanghai, and for my work, for my PhD, I work on understanding coastal land reclamation as a process of building land beyond limit of land resources. So we all know about structures from Dubai, for example. But when I came here and started traveling around China, I saw this massive alteration in the coast, and it's a fascinating topic for me to start. So I started my PhD in early 2016. That was the time when Earth Engine just was launched. But to begin with Earth Engine, I'm an absolute beginner to Earth Engine with my degree in Bachelor's of Arts in Geography. I tried my best to understand JavaScript, to understand geography as a whole, but I'm an absolute beginner to Google Earth Engine. And I try to work it out with fantastic tutorials online. I've tried my best to understand how it will work out. So before Google Earth Engine, I worked on this paper, which is published in Applied Geography, looking into 16 megacities around the world. And this was before Google Earth Engine, and I wish Google Earth Engine was there and I was able to do so, because the idea for me to do was a time series to look at coastal change from 1984 till 2018. But then downloading so much images, and in academia you have a pressure of publishing papers as well. I had to work on this paper, so I took two satellite imagery to look at 16 cities. On the first one is Shanghai over here, which between 1984 and 2018, it has reclaimed more than 500 square kilometers. The yellow line over here is the shoreline of 1984, and the red one is the current one. It's actually not current. It's still it was 2017. And then there are other cities in China. This is Shenzhen. You can see the entire coastline has changed and actually reclaimed from the sea. In Philippines, have reclaimed this entire land for their IT industry. I was also interested in Lagos in Nigeria, where they are reclaiming land for this beautiful. It's an IT complex, again known as Eco Antarctic, and you can check their website. So we worked on this looking at 16 mega cities. But then after that, Google Earth Engine came, and with that, this paper was published in Nature journal, where we're looking at change in the surface water data set. And this was a breakthrough for my PhD, to be honest. And I worked on this data set quite intensively. And I was looking at the transition. If you work on this data set, they have a couple of bands there, and one of them is transition, which basically showing the change between 1984 and 2018. So there are mainly two sub bands which I use, which was new permanent, which basically is a new water pixel. For example, you're digging in a lake, and that lake is new permanent. But I was also looking at lost permanent, which is red here. You can see all these beautiful structures on the coast of Dubai being reclaimed over here. It's basically telling you that there was water in 1984, but in 2015, these are land. So it's basically telling you they are lost. So the basic idea was to flip the entire concept of global surface water. So I'm not using surface water to detect water. I'm using surface water to detect land, but on a water surface. So on the left-hand side, that's Shanghai over here, and there's much of reclamation in the entire Chinese coast for various drivers, for various reasons, and that's what I'm working on as well. But then when you work on coast, you might be aware with this a conflict of definitions between what is coastal zone actually. So I actually decided to use SRTM and have this buffer of 10 kilometers inside land and 10-kilometer out to take it as a coastal buffer, define it as my own coastal zone to understand reclamation. However, this method has certain limitations because when you're taking 10 kilometers, you also take into consider rivers and streams and other water bodies as well. I'm still working on to define coastal zone and how I've come through very close. But when I started working on initially, I was it was beginning. So, but I was able to understand some of the codes, some of the tutorials online, and this was my beginning where I was using my own polygon, and I basically used the reduce to vectors in order to get a vector file, and then I was able to calculate the area of reclaimed land using the global surface water dataset. So if you can see here where I use the transition band, and number 3 is equal to lost permanent, which is basically permanent loss of water bodies, which my case here is a reclaimed land. And this entire black portion over here, which I have displayed here using map.layer, is basically displaying my table and also the results of the KML. And I was able to export this as a KML and then view it on Google Earth, which I will show you in my next slide. I will rather finish my entire slide and I'll quickly go through the code later, but this is how the result comes. So I was able to export a certain portion of the reclaimed land, which was the red one is showing the lost permanent, which is land gain, and the blue one is showing a new permanent, which is a land loss, basically. But then interpretation of these images is very, very important. For example, on the left side here in Tianjin, this red portion here is reclaimed. It's an anthropogenic reclaimed land. It's a land reclamation project. It's the Tianjin port. However, here in Vietnam on left, this is a natural sedimentation. This is not reclamation. This is not by human intervention. There are a couple of ways to, again, look deeper into this to do an object-based classification, because the shape of which we as human construct is very different than the shape when natural features are being formed. When interpreting the water bodies over here in Tianjin, this I know because of my field study. This portion here is an entire aquaculture based. Um, it's completely aquaculture here. So there's interpreting image as a part of my course as a geographer has been very useful. But then I was able to do this for places around the world using using Google Earth Engine and Global Surface dataset. So if you can see, this is Tianjin or the reclaimed land. That's Bangladesh. That's the Ganges Delta. But again, this is reclaimed by nature. This is normal sedimentation. Seoul in South Korea, it's anthropogenic. Here in Singapore, the massive Singapore airport, very beautiful airport, reclaimed by humans. There are a couple of other places around the world where there has been land gain, but the processes are different. Here in Canada, it's just melting ice melt, for example, as an exposure of land. But then you have Mississippi Delta, where some of the places are losing ground here in Sundarban Delta. So I was trying to explain this equilibrium of losing and gaining land, and I was very close to actually publish this as well. But then this happened. It was I was probably 2 months, 1 month's delay, and this paper was published in August 27. And I was speaking with Pradeep that I've submitted this in Nature, and hopefully it comes out. But then this paper was published using the same global surface water data set, and the idea was the same, to flip the entire concept and use the concept of global surface water data set for water. But then also, because it's reclaimed land, to be honest, shoreline, to extract natural shoreline is probably tricky, but extracting shoreline which is constructed by human using very bizarre shapes is even more complicated than you actually imagine. So I've contacted people at Dhritiraj, and they are working very hard in order to understand coastline change and extracting coastline. And I will go through this code very briefly because I'm also trying to understand the code once I finish. But then I was also able to use Google Earth Engine to kind of have this time series very quickly. This is a very quick NDVI time series looking at Pudong district of Shanghai. I am currently very close to here in my university. So this is 1986, and over the years, if you see, um, they have reclaimed quite a bit of land. This is Pudong Airport currently over here, and you can also see the shift of greenness from city center quite in the south of Shanghai. But you can actually see this artificial lake where I'm going next week, probably with my friends to have a picnic. It's an artificial lake built reclaimed over just 4 years. It's just during 4 years or 5 years was reclaimed. So these are a very interesting kind of anthropogenic footprint, which I'm trying to understand, and also its sustainability. But I also want to focus. Thank you to Madhusudan for the last um, Earth Engine community the teacher skills segment, where he explained how can you use a nighttime linear regression of a nighttime and see the trend. I used that same concept for my GPS points, which I took over reclaimed land, and I did a ground validation using street maps from Baidu, or Google doesn't work in China, but I used Baidu maps and my own field photographs in order to understand the land use of reclaimed land. So why you are building land, who are the people living there, how many people are living there. So this map gives an idea of exactly the kind of work which I'm trying to do. So thank you again, the community, to which actually helped me in my project here. And then there, I will quickly move on to show a couple of code, a couple of slides. Some of these things is the Google time slide. Here you can see the reclamation. This is in northeast of China. It's not Dubai. It's northeast of China, where reclamation of this beautiful structure happened around between 3 to 4 years. Same at Shanghai. Right now, I'm here in Shanghai, and this is I'm currently right now sitting here. It's not that far from the coast, but if you can see this reclaimed land over just a couple of years, and it's being the interesting part is that Shanghai is reclaiming more. But even near to the coast, there are a couple of places where nature is playing its role. For example, this island over here is basically a natural sedimentation. It's actually now a wetland reserve for Shanghai, and reserved very, very carefully. But then these are the certain places which has been reclaimed in Shanghai um, over a couple of years. And now if you want to prepare this wonderful time series videos, this code by Andrew is very, very useful. Basically, it's on the slide. You can actually work it out. It's very useful for when you're looking at you're giving presentations. I use quite often. We're looking at, so here in the code we took he took Landsat 5, mask out the clutter with a 25%, and filter it to your geometry. Many of us, we're quite aware with the gaps in Landsat 7. So here's the code itself where you can fill in the gaps in Landsat 7, do it for Landsat 8 as well, have a mosaic of your bands, have a composite, and clip that are into making a collection have a date between 1984. That's what I used, 1984 to 2018, and then you can export that as your as a video over here, right here, and then you can basically show off in your presentations when you're looking at time series. The other one, this one is a bit interesting for me, is working on to get extracting the coastline, and it's very difficult to extract reclaimed land coastline because of two reasons. One is getting, you need elevation model, right? So you're looking at SRTM, but SRTM was launched in the year 2000. Now between 2000 and 2018, Shanghai reclaimed around 300 square kilometers. And when you're reclaiming 300 square kilometers, there is an alteration in the elevation of the coast, which is not accounted for if you're using SRTM. So I just modified this code to use ELOS, which is again was launched in 2011. And between 2011 and 2018, Shanghai has reclaimed around 100 square kilometer, altering its morphology. So getting a proper elevation data set is actually very crucial. So I'm trying to work on how to get a digital elevation model using SAR imagery so that I can have a latest alteration in the morphology, so that I can also calculate its vulnerability and sustainability in the near future. And if you this code from Delta's over here, Edward Morris works with a project in FAST, so we can, well, you can look at their website. But he basically work in Netherlands with Delta's, and there they use OSTO segmentation, where it's a binary image where you're trying to get your thresholds, the lower and the upper threshold, and you're trying to implement that threshold to your image so that you get uh, a very neat coastline of reclaimed land. Just for a trivia, for a question answer round, you can tap your answers in the box in your YouTube. The image will appear. There are a few certain dots over here. What do you think those dots are? It's just a game for image interpretation. But then this is using Sentinel images. These are the dikes which are being constructed so that the sediment comes and fill in, and you have a new reclaimed land over Shanghai. This is an image of month of March when I was there in my field. I can change the date over here, and I can get the image. I can change the date over here, and I can get an image actually of last week and see what is the progress. So you can actually export this as a vector file and get your proper coastline over in reclaimed land. But it's fascinating that I actually can view all these dikes, and these by the end of by the time I finish my PhD, this land will be reclaimed, and that there will be an artificial wetland. Yeah, so that's the question. What do you think these are? Tap in your answers. Earth Indian community will give you chocolates. So that's about it, to be honest. These are the 13 things which I'm working on. The last slide is basically when I was in my field. There are certain villas on the reclaimed land, so they're land being reclaimed for a very posh class of our society. And this was the billboard in order to buy one of those villas, and it says 71% of the earth is covered by sea, only for a few people. That's very interesting a concept which I'm working on and trying to understand why we are building land. And it's not a Chinese concept. It's happening in Jakarta. It's happening in Singapore, Malaysia, all the South Asian cities. So it's a very interesting topic to look forward, especially in the era of sea level rise. I hope I've not taken much time, but I will stop over here. Um, Greg, what do you think?
Yeah, that was fascinating, Dhritiraj. Yeah, I mean, taking a look at even the surface water data set and seeing new applications for how people use it. Uh, the flipped image and seeing new land, that was something that blew my mind, because I know I'd known the data set for a while, but that's definitely something new and interesting. I don't
Yeah.
know if we have those chocolates that you promised people, but let's see if people have answers to come up.
I
Uh,
hope there are some answers over there.
yeah, thanks a lot for that talk.
No, yeah, yeah.
Um, yeah, so let's come around now to Pradeep. Pradeep has put together an intro on SAR imagery, and he'll help you figure out how to get started with that. Pradeep.
Yeah, thank you. Thanks a lot, Craig. So for today, I've been learning a little bit about SAR imagery myself for some of the work that I had to do, and like Craig mentioned, there was some interest on the forum as well about SAR imagery and some applications using it. So based on my own experience as well as some of my colleagues that I run into often, I've noticed that SAR imagery is it's quite different from optical imagery that we are more familiar with. We often work with Landsat imagery or Sentinel-2, which are all optical imagery. Um, SAR imagery are very different from that, and trying to understand how it is different and what it is useful for and all of that. There's a bit of a learning curve for that, was my experience. So I've just been doing some digging around, and based on what I've learned so far, I just put together a few slides with some basic introductory concepts that 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 can help us understand how SAR imagery is different from optical imagery, and what are some of the key concepts to keep in mind while thinking about using them, and where there might be difficulties. So I'll switch over to my slides. Okay, so this is just an introductory few slides on the basic concepts of radar imagery and synthetic aperture radar imagery. To get started, so like I was saying, we are familiar with Landsat imagery, right? So so just excuse me, this is a little, this is a small image on a slide, but the point here with this figure on top is all the Landsat satellites so far. This figure shows the various bands, various wavelength bands that the Landsat sensor senses. So if you remember all those bands that each of the Landsat image has, they all come from different parts of the electromagnetic spectrum, like it is shown in this. So the horizontal axis is the wavelength. So there's band 1, 2, 3, 4, 5, 6, 7, and so on, all the Landsat bands as well. So this is the range of wavelengths that Landsat bands covers. But if you think about the electromagnetic spectrum, that has a much larger span, right? The wavelength goes from much shorter wavelengths and gamma rays and all of that, and much longer wavelengths like in radio waves. And here, right here, is the microwave band. All the microwave signals are in this range of wavelengths. And if you notice, somewhere in the middle here is the visual spectrum, which we see as humans, and they form part of the Landsat bands as well. Now, if you think about it, so the Landsat bands, which go from about 400 microns, 400 nanometers to about 13,000 nanometers in this figure, they map to just about this range in the electromagnetic spectrum. A little bit of the infrared and a little bit of the visible spectrum. As you can see, the microwave bands are entirely outside of that. So Landsat bands, the range of electromagnetic spectrum that the Landsat satellites sense, are entirely outside the range of wavelengths that the SAR imagery captures. So that right there is a fundamental difference between Landsat bands and SAR bands. And I don't have the data here for Sentinel, but the comparison would be somewhat similar even for that. So the take home is that optical imagery in satellites, they span a range of about this much, and that is entirely different from the range of electromagnetic spectrum that SAR bands capture. So just a little deeper into how radar and optical imagery compare. So on the left is the highlights about the radar imagery. For example, radar imagery, just simply because of the fact that they are in the microwave range of the electromagnetic spectrum, they are much less affected by atmospheric effects, which is very different from optical imagery. I'm sure any one of you who's worked with Landsat know that atmospheric effects have to be corrected before you can start using the surface reflecting products. So going from raw captures of the Landsat imagery down to the surface reflectance, there's a lot of atmospheric effect correction that needs to be done before they're useful as surface reflectance. But like I said, radar imagery, they have almost very minimal atmospheric effects. The other important thing to keep in mind is radar imagery is active sensing, while Landsat and other optical imagery are passive sensing. And the key point here is that optical imagery, the satellites just fly by, and the sensors are just sitting on the satellite and sensing the electromagnetic radiation signals that they sense reflected off the ground. So they're just passively sitting there sensing what falls on their sensors. But radar imagery, they are active in the sense that the satellite, as it is flying by, it actively emits radar imagery, microwave energy, and it waits to sense the reflected signal back from the ground. So in optical imagery, there is no transmission of any signal, but in radar imagery, radio waves are actively transmitted from the satellite, and the sensor is waiting to pick up the reflected energy from the ground. So in that sense, that also is a very significant difference between radar imagery and optical imagery. Moving on, so the other important difference is that radar imagery, because again of the wavelength of the signal used, they are all-weather imagery and day and night capabilities, since they don't depend, for example, on visible light. They can see even at night, and since they don't depend on visible light, clouds don't interfere with their signals as much as clouds interfere with the optical imagery. So because of those two effects, the radar imagery can see through clouds, they can see at night, but optical imagery, of course, as you all know, they can't see through clouds, and of course, not at night as well. The radar imagery, the actual signal that we are working with at a pixel level, they are what are called backscatter values, and this backscatter is sensitive to target properties. In ways that are different from optical imagery. We'll get into a little bit of detail about this, but I just want to put it up there here as one of the key differences between radar and optical imagery. So radar imagery depends on backscatter, and the backscatter depends heavily on the target properties on ground, like for example, structure and dielectric properties of the target. There are a few disadvantages of radar imagery as well. A few of them I've listed here. The data basically can sometimes be hard to interpret. And this is particularly so for many of us who come from having worked with optical imagery more, and since the data in radar imagery is fundamentally different in the way they're captured. Yeah?
Sorry to interrupt. Let's try to figure out this technical issue.
Yeah.
You're presenting your screen, but for some reason on the YouTube live stream, it's not showing up as the main window. I've tried to present to everyone, which is what I normally do.
Is
But
this
it's
better
not,
now?
no, I'm not sure if it's something on your end.
Okay.
As an intermediate sort of solution, Dhritiraj, if you're there, can you share your screen, because the live stream seems to be showing your window.
All right, I will do that.
Yeah, okay.
Okay,
Which
so right now, Dhritiraj, I'm on the slide titled Radar versus Optical Imaging.
Okay.
Yeah, and just hit space one more time so that the disadvantages at the bottom animation also shows up.
Yeah, we see the
It is.
slides. So
Okay.
Oh, okay, great. Thanks, Craig. So I'll continue. So all these slides are. I hope you are able to follow along since you have the link to the slides out there, all of you in the audience. So moving on. So like I was saying, there are a few disadvantages with the radar crossing as well. Some of which is largely because many of us come from thinking about remote sensing from the optical space. So it can be hard to interpret. Some technical reasons why there might be difficulties in interpreting radar imagery is the sensor is side looking. And like I said, there are topographical effects on the signal that's received. And also there are sources of noise like speckle noise. So we'll get into a little bit of detail about all of this, but again, I just wanted to put it all out there in one slide about the main comparisons and some of the disadvantages of radar. So next slide, Dhritiraj. In this slide, there's a figure, there's a cartoon. So there's the cartoon on the left and the right. So this is how SAR imagery is captured. You can think about it as a shuttle that's flying over, and it has a sensor and a transmitter. So the transmitter transmits the radio waves, and the sensor receives it, and that's the sense signal. So what's on the left is, let's say the shuttle was transmitting top down, like so if it was looking top down and it was transmitting also top down. So you can see that if there are two targets A and B on the ground, then the time that the signal takes to go and get reflected back from both of those targets are the same, right? So from A, it might come back at time t0. It will come back at time t0 from B as well, because the distance from A to the shuttle is the same as the distance from B to the shuttle. The thing here to note is, since the SAR imagery depends on radar, radio waves, microwaves, what it is really sensitive to is phase differences between the transmitted and the received signal. So here, if you were in the scenario on the left side, when you transmit the signal and you receive, you sense the received signal from A and B, and if they are both at the same phase, then you won't be able to detect the difference between the two. However, if you think about it like on the scenario on the right, which is the signal is being transmitted in a slanting direction, the shuttle is still flying over the ground. It is transmitting the signal in a slanting direction. Now, if you think about it, this time the signal will take to go from shuttle to B and back is much shorter than, okay, not much shorter, but shorter than the time the signal might take to go from shuttle to A and back. And so if the difference in time is delta t, then the radar imagery, the sensor is in fact latching on to the information in delta t in its sensing. So it's all about detecting phase differences, and that's how you detect different features on the ground. So if you are not able to detect the phase difference between two features on the ground, like in the scenario on the left side, then you can't tell them apart in the imagery. But if you are able to tell the phase difference apart between two targets, like on the right side, you will be able to tell the two targets apart. So this is again, this is one more fundamental difference about how optical imagery and radar imagery are different. Radar imagery, it actually looks for the phase differences between the transmitted and the received signals, and so that's a fundamental reason why the shuttle also has to look in a slanting direction, and that is a fundamental part of how radar imagery is sensed. And like we'll get to, there are a couple of consequences of this as well. But for now, the point to note is optical imagery are typically down-looking sensors, but since the electromagnetic spectrum that they operate in is very different, that's okay for those, but for radar imagery, that doesn't work because they won't be able to resolve targets that are at equal distances from the shuttle. But that can be fixed by looking in a slanting direction, which is what the SAR data does. Couple of points to note: the larger the antenna on the shuttle, the finer the spatial resolution on the ground that it's able to latch onto. So you can think about it as an aperture. So if the aperture is large, you would be able to decipher smaller resolution, finer resolution on the ground. But also, if you can think about it, there will be practical constraints on how large an antenna you can mount on a shuttle. So in order to not be limited by that, scientists use complex signal processing techniques and motion of the shuttle itself and all of that to synthetically build a large aperture sensor. And so that's where the synthetic word in the synthetic aperture radar comes from. The aperture that actually manifests is synthetically derived, and it's much larger than the physical antenna that sits on the shuttle itself. Now, getting into a little more details, Dhritiraj, can you go to the next slide, which is called main aspects of SAR imagery? So in this, I wanted to highlight a couple of main aspects that determine how the signal turns out. So the sensed imagery turns out. So the two main aspects are transmitted signal and the target characteristics. Transmitted signal, there is the wavelength, polarization, and the incidence angle, and target characteristics, there are topography and roughness of the surface and dielectric constant of the target. We'll get into a little bit of details with each of them. But the wavelength and polarization of the transmitted signal will determine the scattering from and penetration into the target. The incidence angle of the signal will determine the image brightness. Target characteristics, of course, determine what the backscatter is. That's how you think about the reflected signal in radar terms. So the backscatter from the target is determined very strongly by the topography, surface roughness, and so on, and dielectric constant of the target. Next slide, main aspects of the radar signal. In this case, in this slide, the transmitted signal characteristics. So here's a picture showing wavelengths, increasing wavelengths on the horizontal axis and different targets on the vertical axis. If you think about it, the larger the wavelength, it turns out the penetration into the target is deeper. So as you use higher, longer wavelength signals in your radar, you will be able to sense characteristics of the target deeper and deeper under the surface of the target. So low wavelengths, the reflection and backscatter will be from the top surfaces. Medium level wavelengths, they'll penetrate a little bit, and long wavelengths actually penetrate quite deep into the target. So this has so depending on your application, you might use different wavelength radar imagery. So it might be whether it is dry snow, whether it is alluvium or vegetation characteristics. You might want different wavelengths for different aspects of those that you might be interested in. So for example, if you want to just detect forest presence versus absence, you might use one particular wavelength. If you want to tell forest types based on vegetation structure and all of that, you might want your signal to actually go deep into the vegetation structure to derive information from there. So you will use another wavelength. And similarly, you might be interested in soil characteristics, features deep under the soil, so snow characteristics and features deep under the snow melt, and so on. So different applications take different wavelengths. Also, there is the concept of polarization in radar. That's also a whole world in itself. I didn't want to get into that now because of it would be beyond the scope of the introductory material I have here. But that's another thing that is worth getting into as well. This is again polarization of electromagnetic spectrum. If you remember from your high school days, it's basically the same thing: horizontal and vertical polarization at transmission and receiving phase. So depending on which combination you use, you will have different information sensed as well. And of course, there's the incidence angle, which affects the image brightness. The other aspect is the target characteristics aspects, which is in the next slide. Main aspects, target characteristics. So this will determine the various backscattering mechanisms. On the right side is the cartoon showing some 4 main different kinds of backscattering. So if you have a smooth surface, the reflection might be almost perfect reflection, and that will be specular backscatter, because hardly anything comes back into the signal, into the sensor. Almost everything reflects away from the sensor. If you have a target which has 2 phases to it, the transmitted signal may bounce 2 times off of the 2 surfaces and come right back, and much of it will come right back. So this might look quite bright in the image. That's double bounce. If you have a very rough surface, of course, the signal will scatter in all directions. Only small part of that will reach back the sensor, and that is rough surface backscattering. And in some cases, the signal will penetrate deep into the target, and depending on the structure of the target, it will scatter multiple times within the target itself, and then some of it will come out and come back into the sensor, and that's volume scattering. So these are 4 main kinds of scattering that you might encounter at surfaces on the ground. All of this is also all of these are also interact with things like density of the target on the ground, dielectric constant on the ground of the target on the ground. This is basically how much water content there is in the target, the size and orientation, and of course the wavelength of the signal that we've been talking about. So the dielectric constant, which is the water content, affects the absorption of microwave energy and hence affects the backscattering. Next slide, which has additional factors that also influence the signal sense that is sensed. These are advanced topics. I didn't get into the details of them, but I just wanted to put them here so you can explore them in your own time. Additional factors that determine the signal that is sensed is distortion and noise. Like all transmission and sensing systems, there might be distortions due to geometrics and the radiometrics of the optical system. So radiometric is basically signal might be of different strengths in different parts of the swath. So the transmission and reception will be different depending on where in the swaths the target is. Geometric distortion, this is mainly because the slant direction, the look direction is slanted in radar imagery. So that will lead to features like slant range distortion, layover distortion, and layover and foreshortening, shadows, and so on. And then there's the other source of noise, which is speckle noise, which is basically because of multiple constructive and destructive interferences between the scattered signal from the target. These are all so radiometric and speckle noise and the causes for those, and all those might get into details of electromagnetics and so on. Those are beyond the scope of this talk, and also beyond this. I'm not an expert in those. But geometric distortions, these are more geometric, and if you think about the imaging angles and so on, these are easier to understand. You could check these out in your own time. Lastly, I wanted to leave you with just some broad hints on so we talked about how different wavelengths are used for different applications. All the concepts we talked about so far are common to whichever wavelength you might use, so it doesn't depend on which wavelength. All of these concepts apply for all of them. But when you think about your application, you might want to think about what wavelength you want to use. And here is a table that's indicative of that. So it could go from low frequency, high wavelengths to high frequency, low wavelengths. And here's a table. So for example, if you're interested in agriculture and surface characteristics of forests and soil moisture and all that, you might want L band, which is in this frequency range. If you want to think about agriculture and ocean, it will be in this range, and then so on, glaciology, forest biomass, and things like that. commonly used bands for forest vegetation monitoring, for example, is L band. Forest structure, the canopy structure would be C band. X band is even shorter wavelength, so it would reflect off of the top of the canopy. And just as a pointer, you might have heard of datasets called Sentinel-1 and Pulsar. These are both radar imagery. Both of these are available as datasets in the Earth Engine catalog. Sentinel-1 is the band, it's a C-band radar, and it's more for ocean and agricultural applications, and Pulsar is more for forestry and soil moisture and stuff like that. I just want to leave you with a whole lot of resources that's out there that's excellent. In fact, much of what I just now spoke and much of what I have understood about all of this comes from these resources, and I would highly encourage you to go back and check these out in your own time. There's Earth Observation College, which is like an online resource page. So here's the link to that. And the same people have a YouTube channel which has multiple short videos on topic-wise. They're organized topic-wise. And in fact, if you go back to the original website itself, the eocollege.org/resources, there's a huge range of full-length webinars and video tutorials running up to 45 minutes, 1 hour, which go in depth into the basics, the techniques, the processing, applications, and all of these. I highly encourage you all to go in there and take a look. And lastly, just a few additional resources with documents, written stuff. So there's the recently released Surveyor SAR handbook for forest monitoring and biomass estimation. The link is all embedded in there. There's a technical report from WWF which talks about satellite remote sensing for conservation. This has both optical as well as radar. And then there's the real technical, the paper that describes the full technicalities of the SAR imagery, which is also linked in here. That's about it for these slides. I will stop sharing and hand it over back to you, Dhritiraj. Craig, sorry.
Yeah, thanks a lot for that, Pradeep. Sorry for the technical difficulties, but I think that was definitely a very informative tutorial for anyone who wants to start out. And I would definitely encourage users to check out the resources at the end that Pradeep has shared. I've gone through them myself as well. They're a very good place to start. If anyone has questions for either Pradeep or Dhritiraj, you can please enter them into the YouTube live stream. We have one question for Dhritiraj, which I will ask him right now. So, Dhritiraj?
Yeah.
Yeah, so could you read out the question and take a minute to reply?
So I need to go to the YouTube channel.
No, it's the same one that you see at the end of the slides.
Okay, yeah. So Gunit was asking, was trying answering. These are dots or ships or boats or small islands. Well, they are actually wind mills. So it's a complete set of wind turbines on the coast, generating renewable energy for Shanghai. But they're quite nice. A good try, Gunit. Arinud was asking, that's a fantastic question. Now, we always talk about, this is the main problem when we're working on coast. So the tides are, tide ranges in Shanghai are up to 4.5, 5 meters. So that's a lot when you're calculating coastal change and coastline change. But because I'm working on reclaimed land, I'm looking at construction. So these construction happen over in China. I'm talking about Chinese speed. So these construction happen over over a year. So in order to assess that, I'm taking annual composites or 6-month composites to look at what sort of construction is coming up and the land use. But yeah, as I work on future, as I'm looking into the sustainability of these reclaimed land and related to sea level rise, I need to consider the tides and I have to rectify the error in the calculation based on tides. So yes, I know. Let's work in the future for that as well.
Yeah. Uh, thanks. Thanks for that, Dhritiraj.
Yeah.
Pradeep, you had a suggestion?
Yeah, thanks, Greg. Yeah, so I was thinking I'll take a minute since what I talked about might have been a lot of information to absorb in one go, and then questions might take time. And then I'll just take a minute to go to the website that I pointed to and show what exactly I meant by lots of resources being available. So I'll just share my screen again. Um, yeah, so I'm on the Earth EO College resources page, the link that I had shared on the slides. So if you come in here, this is so there are various categories on the left: methods, basics, applications. There are English and Spanish ones. There are books, software, stocks, tutorials, units. So if you click
Yeah,
on basics,
Pradeep, I
yep,
think it's the same problem as before.
okay.
We are unable to pin you to
Uh,
the video. So
is it okay?
is it the same? No, it'll take a lot of browsing, right, to go through if the Dhritiraj had to do the same thing.
Yeah, I think so. So has it have we gone? Is my screen visible now on the stream? You think?
Okay, wait. Yeah. It's come now. It's come
Okay.
now. Okay, go
Okay.
ahead.
Okay. Yeah. So I was saying. So this is the link from the slide that I had shared. So if you come in here, so there are multiple categories, methods, basics, and all of that. So I just click basics. So if you can, I can go down here and say English while So this is filtered down. So basics of R. So it's one of these that I went over in detail for my own learning, and I borrowed a lot from that for my own talk just now. But if you can see, there are all these technical aspects of the basics of SAR imagery itself, which have multiple YouTube videos. So if you click on one of these, I'll wait for it to load. But if you also want, let's say, applications hydrosphere, I'll there's agriculture, snow cover, biomass, crop type classification. Each of these is so if you look at this basics of SAR thing, this is a webinar with slides. This is a full 1 hour long webinar. There is tutorials on crop classification, all of these things. So you can browse through this, and there are tens of videos that have excellent content on SAR imagery, starting from basics through processing all the way through to applications. So I just wanted to show that. I think I'll stop sharing the screen. That's all I had. Thanks, Greg.
Yeah. Thanks a lot for that, Pradeep. So we are pretty much nearing the end. For the attendees who were not there for the initial bit, I'll just send out a reminder and quickly share my screen here. We do have an open call for volunteers to the Earth Engine India community. So these links are in the presentation for today, and they will be shared by email again later today. There are several open positions for the Earth Engine India community. So community organizers to oversee the growth of the community, the Earth Engine India Media Committee, that helps get in touch with the journalist community, the media community in the country. Community on air hosts who would help curate these monthly webinars that take place. Code curators who could help come up with example scripts for the community repositories for people getting started in Earth Engine, and also website managers. So if you guys have come across this Earth Engine India users community website, we're also definitely in need of someone to help us manage that website and keep it up to date. So feel free to check out this form and fill it out. It's not very detailed at all. It's just your email ID, what positions you would like to apply for, and what motivates you to join the community. Don't be intimidated by this process. Um, this is not a interview process, or it's open, and everyone, we're open to anyone joining in, pitching in, and being a part of the community in a volunteering capacity. So I think I will end here today. Thank you all for attending. That was a really good webinar, and looking forward to seeing you again next month, in a month. Thanks, Dhritiraj. Thanks, Pradeep, for your presentations. Thanks, Madhu.
Thanks, guys.
Yeah.